The cluster brings together people from Vancouver and the Okanagan to share about these things. 2 bits. Subscribe to our mail list. You probably may have got this from our mail list. We use the mail list to disseminate more than just the seminar stuff, but it's very low traffic. It's also used to give an idea of who wants to be interested in our activities, so we can direct programming in that space. We also capture our seminars, and there's a whole cluster of those on YouTube if you're interested in past seminars within our series. I recognize that we are drawn together today in person, at least, on the ancestral and unceded territory of the Musqueam people. Importantly, for all of these activities of learning, we recognize that learning and community building was shared amongst people here since time immemorial. Just to flag that we have announced the fall training school. So this is a 3 days activity focused towards grad students, postdoctoral researchers, research engineers, etc. We'll have introduction to all the major methods, but we'll also have some advanced programming, learning about mass spectrometry and a whole range of other bits and pieces. It's coming together really nicely. We've just, I think, confirmed our 2 plenaries are pretty much signed up. They're really exciting. I'm not going to break the secrets of those yet, but there's some really cool people coming in from a few fun places in the world. Importantly for this year, though, we also have that trainees will be able to present not only posters, but we'll have oral abstracts. We expect this to be competitive. So if you're interested, please make sure you submit your abstracts so we can adjudicate and make sure we have a good program on that. And the other fact after today's, we'll have a short break, but the seminar series will resume in the fall. Right. All right. So it's a great pleasure to introduce my colleague, Professor Karthik Akkiraju, who's an assistant professor in the Department of Materials Engineering. And I would say one of the exciting aspects brings not only state-of-the-art science and engineering, but thinks about how this is important in the world around us. And I'll let him talk a bit more about why that's of interest. But please take us away, Karthik.
Awesome. Yeah, thanks, Ben, so much for inviting me, and Joey for organizing this talk. I'm super excited to be here and share some of my lab's work on using Operando Spectroscopy for heterogeneous catalysis research. To sort of set this talk up, what we are interested as a lab is looking at surface reactions. So we are interested in converting low-value reactants into higher-value products, and then figuring out how exactly does this transformation occur. And a lot of that transformation occurs on surfaces, and hence we want to figure out what exactly is going on, and we want to understand all of these processes at the same time. So we use a bunch of Operando spectroscopy techniques, which I'll go into detail in the next 40 minutes or so. So that's sort of the broad overview of what I'll be covering today. So why is this important? Why is chemical transformation as a process interesting? So here's a breakdown of CO2 emissions for the 3 big sectors of iron and steel on the top here, the cement manufacturing, and here's the chemical commodities we are interested in. So roughly speaking, all 3 of these account for about 6 gigatons of CO2 yearly, which is roughly 20% of the world's CO2 emissions, out of which 2 to 3% comes from chemical manufacturing. So this is production of molecules like methanol, propanol, ammonia, which go into a lot of the commodities that we see in this room, for example. A lot of the plastics, a lot of household supplies, all of those are a product of about 1 ton of CO2. So where is this 1 ton of CO2 coming from, right? So what are the energy-intensive processes within this manufacturing? So roughly speaking, 50% of that comes from heating. So using natural gas, coal, or any other fossil fuel-based heating sources accounts for 50%. And the other 50% is process inefficiency. So you're trying to convert, let's say you start from CO, and you're trying to convert it into a higher value product. And the end product usually tends to be CO2 because that's a thermodynamically more favorable product. So our goal is to selectively form some of these products so that we can cut down on that 50% number. And if you look at the long-term trajectory for how we would reconcile with these numbers, in the next about till 2030, the idea is usually to rely on existing processes. So how do you make existing processes like more efficient? How do you design better catalysts would be one way to do this. And in the more medium to long term, the goal would be to combine this process efficiency with alternate feedstocks, whether it be biomass derived, CO2 derived, and then being driven by renewable electricity, so to sort of close the loop on getting from where we are to net zero. So that's the overall narrative of why we are interested in catalysis for chemical feedstock manufacturing. And what catalysis generally involves, if you really zoom into the atomistic level, is designing these particles so that they'll accelerate the reactions that we like. And typically, if you imagine this to be a catalyst particle, there are numerous surface sites. So there are edge sites, there are planar sites, there are different type of facets, and each of them coming with their own reactivity. So the goal usually is to figure out which one of these are most suitable for the chemical reaction we are interested in. And that just forms a part of the picture. So you have modeling of adsorption processes at the atomistic level, but then you want to integrate that with diffusion at a next time scale, and then ultimately heat transfer, mass transfer, and other transport limitations that would kick in at higher time scales. So for today, we are predominantly interested in the atomistic picture of how you would tune some of these atomic positions, sites to enhance your reactivity. But towards the end of the talk, I'll also talk about including transport considerations into this atomistic picture. So to start off with, let's say a 101 approach, how do you design catalysts, right? If you look back into history, one of the most famous examples is that of ammonia production. So this is going back all the way to the 1900s, where there was a food shortage. So the population was growing, and there was a real concern that the world is going to run out of food, and there was no way for us to synthesize ammonia, which is the artificial fertilizer, to increase crop production. That's where BASF, the chemical company, came into the picture, and they tried about 2,500 catalysts, 6,000 different experiments to figure out if there's a magic material that would take nitrogen, hydrogen, and put it together to form ammonia at a reasonable cost, temperature, pressure, everything else considered. And nothing worked. And this is a direct quote from Alvin Mitash's paper, where he said, ultimately, they had a piece of rock, literally from Sweden, that was sitting on a bench, and they randomly decided to put that in to the reactor chamber, and it worked. And even to date, it is this iron oxide-based chemistry that is used for commercial production of ammonia. And this approach is traditionally called an Edisonian or a trial-based approach, where based on either your intuition or just luck, you find the magic material that lets you run the reactions that you like. So obviously that the field has moved on from this, or tried to move on from this, to figure out more so-called rational approaches to catalyst design, right? So without having to rely on chance discovery, how do you do this in a more carefully thought out manner? And that's where a lot of the earliest studies in catalysis have relied on what we call as model studies. So for example, if you think about the universe of possibilities of different catalysts, take all the elements in the periodic table, you have about 10 power 60. And typically based on human intuition, it's sort of a misleading word, but it's usually based on experience or literature. You narrow down the possibilities to a smaller subset, and then you design experiments, carefully designed experiments. You may do 1 a day, 2 a day, and you gather some fundamental insights. So to give an example of what this looks like, here is the same reaction that I was mentioning earlier about nitrogen dissociation, right? How does nitrogen react on surfaces? So you could take a really well-defined ruthenium 001 surface. So this is one of the flat surfaces, and you can see the reaction rate here. And then the hypothesis is that it is these step sites that are responsible for generating the catalytic activity, right? So the turnover frequency that you see here is because the atoms are the ones that are responsible for nitrogen dissociation. And the way you would test this hypothesis is you could selectively deposit gold atoms on these ruthenium, next to these ruthenium sites to block them. And then you see a tremendous drop in activity, right? So this would be an example of a model study where you have a hypothesis, you go, you test it, and now you know in order to maximize your nitrogen production, you need to have more of these step sites. But the challenge with this approach is it's not transferable, right? One has to painstakingly do these experiments for every single reaction that you might be interested in, and then it'll be really difficult to transfer these to real catalysts that are really messy. So these are perfectly made surfaces. So that sort of leads us to what is often referred to as the descriptor-based approach. So the descriptors are physically meaningful parameters that will help you gain insight into why a catalyst would work. So here's one example looking at the same reaction again, nitrogen dissociation. Now, instead of creating the surfaces like in the previous example, what this particular study did was you compute the position of the D-band center of different metals. So transition metals usually have a half-filled S-band, and then also the D-band filling varies depending on where you are in the periodic table. And the trend that's shown here is that as the D-band center moves up relative to the Fermi level, your adsorption becomes stronger and stronger. So if you want a catalyst that really strongly adsorbs nitrogen, you choose something like an RE here. Or if you want something that really weakly adsorbs, you choose the silver here. And the magic usually lies in between, where it's called the Goldilocks principle, so where you want something to not stick too strongly or too lightly. And not just nitrogen dissociation, but most industrial reactions use some of these catalysts. So you want a D-band center that's somewhere in between so that you have reasonable adsorption and desorption. And you sort of see the power of this approach, right? So it's a really simple parameter that's easy to compute. You don't have to run all the experiments that we saw previously. And you have reasonable physical intuition for why this works, and also reasonable reasonable predictive capability. So in the future, you could target a lot of your validation experiments around nickel and cobalt. And this is just a very specific example. So over the years, there's been a lot of work using different types of descriptors. So you could, all the way from Sabatier about 100 years ago, where you just looked at bond dissociation energies, all the way down to maybe about 5 years ago, where you could just count the number of electrons or coordination numbers and explain reactivity. The challenge with this approach is, going back to the original reason why we started this, is it's simple. So you have something that's easy to compute and explain. And that works pretty well for small molecules. So if you're dealing with nitrogen, carbon monoxide, oxygen, hydrogen, water splitting type of experiments, these things are easy to establish and validate. But the real challenge lies in some of the industrial reactions that I mentioned in the beginning. If you're dealing with large carbon molecules, you have multiple adsorptions, multiple products that you have to carefully go through competing reaction pathways and gather spectroscopic evidence. So that sort of forms the motivation for the 3 of the studies that I'll be describing today. So we really wanted to move from some of these simple molecules to talk about industrially relevant carbon-containing larger molecules. So I'll talk about 3 examples today. So the first one is methane. So methane is usually highly unreactive because the CH bond is one of the strongest in physical chemistry altogether. So breaking that bond is really challenging. So I'll talk about some of our experiences there. Formaldehyde is an indoor air pollutant. So converting formaldehyde into something that's less harmful is one of the goals of this project. And finally, DME is a solvent in lithium-ion batteries. So I'll sort of take a departure from catalysis and show how some of the descriptor-based approaches developed in catalysis can be applicable to other contexts as well. And the goal overall is, again, trying to come up with descriptors that can explain some sort of a physical reactivity or performance. And this can be used as a predictive tool to identify better materials once we validate these. Right, so for that, I'll use three main techniques throughout the talk. So I'll talk quite a bit of in situ spectroscopy, so both using X-rays and IR. And then I'll spend some time also talking about using theory, density functional theory, to explain some of the reaction mechanisms that we find in our experiments. And then finally, validating the performance using kinetic measurements in a flow reactor. So that sort of forms the crux of what I'll be talking about today. So physical origin of methane activation, how do you design manganese oxides for formaldehyde oxidation, and then looking into cathode reactivity. And then towards the end, I'll talk a little more about how machine learning and AI models have accelerated and almost sort of replaced some of the techniques that I'll be talking about in the earlier parts of my talk. And then finally, I'll end with thinking about beyond active site engineering. So what else can we do in catalysis that's not just optimizing for performance? All right, so the first one is looking at the origin of low temperature methane activation. The reaction we are interested in is taking methane, which is CH4, and first activating it. So activating means breaking the first CH bond. And then once you break the bond, then you can convert that into more useful or less harmful products. And this has been similar to a lot of problems you see also. It's been referred to as a holy grail of chemical catalysis, in that it's a really difficult problem to solve. And back in 2017, there was a lot of theoretical work trying to understand what is the best material for this reaction. So here's the result from that study, where they explored a bunch of different catalysts, right? So oxides, metals, metal organic frameworks, composites, and they ended up with iridium oxide being the one with the highest activation rate. So that was a theoretical prediction, and then we wanted to go in and understand why is that iridium oxide works. So we took a closer look at the iridium oxide surface. So here's what the surface of iridium oxide looks like, and you have different species here. So you have what we call as the coordinatively undersaturated oxygen, or the CUS oxygen here, and we have a bridge oxygen. So they're just differently coordinated oxygens on a iridium surface, and then of course you have the corresponding iridium atoms as well. Now the question is, which one of these species is responsible for the high activity that was predicted in the theoretical modeling exercises? So for this, we turn to Operando ambient pressure XPS, so where you could look at both the reaction intermediates, but also the surface structure at the same time. And for those who are familiar with XPS, so this is what an oxygen 1s spectrum would look like from an XPS. And you would notice a really peculiar feature in this XPS spectrum in this one at 529 eV. Typically, as you would expect that the earliest peak would be a bulk oxygen peak, and every other oxygen peaks would be towards the left of it, related to either hydroxyls, carbonaceous species, whatnot. But we are really curious about why a tail would show up in the spectrum, and we want to understand what exactly leads to this. And this is where we turned to density functional theory to figure out what is the fingerprint of this. So here's the oxygen density of states that we computed, and then we see that close to the Fermi edge at close to 0, there is a spike of oxygen CUS species. So this is where we started to think, could this be a signature fingerprint of the oxygen cut species. And then we also looked at the valence band, where again, this is before cleaning and this is after cleaning. So cleaning is where we remove any carbonaceous impurities that form in the reaction chamber. And we see that these species become more clear after clearing. And then similarly, the valence band edge also spikes up, suggesting that this feature belongs to a special oxygen feature that only shows up for rutile oxides. Now the question was, does this species actually contribute towards reactivity for methane? Right, so in these operando experiments, the cool thing is that you can change temperature and you can also track the products that come off when you run these reactions. So here we ran the reaction from 125 degrees all the way to 425 in a methane environment. And this is the carbon 1s spectrum. And what you can see is that at 125 degrees, you form carbon-containing species, which means that methane has been broken on the surface, activated, and you have reaction intermediates corresponding to what happens when methane reacts with iridium oxide. So you have two different intermediates here. And then as you heat up to 425, at 425, you see a flat line indicating that all the reaction intermediates have been converted. Another question is, where do they go? And within the setup, we are also able to track the gaseous products using a mass spec. And we see that by the time we get to 425, you have a lot of CO2 being formed and also a minor amount of CO, suggesting that iridium oxide was able to not only activate methane at a relatively low temperature, but also lead to complete conversion to CO and CO2. So this is only part of the story where we saw that we identified the active species as being these oxygen cut species. We showed that they survived the reaction and still are available at 425 degrees. So what do we do with this information? That's when we said, can we design new iridium oxides which have a higher content of these oxygen cut species? With the idea being that if we have more of these species, we could lower the temperature for methane activation. So the one shown in gray is the one that we had been working with so far. And then we designed two other iridium oxide species, the one shown in blue and red here, with higher iridium and oxygen cut species. So we characterize them using, again, XPS and then XRD to make sure that we do have these cut species. And then we want to test them out in a reactor setup to see if we could activate methane at a lower temperature. And here are the results for methane activation at room temperature. So the iridium oxides, earlier, we could run them at 120, 125 degrees and see that methane was getting activated. But this room temperature result here shows that you already have conversion to CO2, even at room temperature with these two new oxides here. And we wanted to see if this is really true, if methane was really getting activated. And then we turned again to IR spectroscopy now. And we could see the formation of reaction intermediates starting all the way from 20 degrees onwards. Going to 250, we see a strong formate peak, which is one of the major intermediates in the methane reaction pathway. So based on this, we were, one, able to identify the active species for why iridium is so good with methane conversion. And then I won't go into the details, but we are also able to propose different pathways based on the different reaction intermediates that we saw, both in the XPS experiments as well as lab scale IR spectroscopy. All right, okay, that sort of brings me to the second example that I want to share with you, which is around designing manganese oxides for formaldehyde oxidation. So as I said, formaldehyde is an indoor air pollutant. So a lot of the woodwork that you see has resins which give off formaldehyde because of the way they've been treated. And if you let them sit in your household, they emit a lot of these VOCs, of which formaldehyde is a big component, and they are potentially carcinogenic. So the idea is that instead of using an air purifier, which usually has an active carbon which absorbs a lot of these pollutants, can we use a catalytic process instead? Because with an adsorbent, it'll run out at some point because it's like a sponge. And in a few months, in a few years, you'll have to replace it. But if you are running a catalytic process, in theory, you could run it for much longer because it is catalytic by design. Right? So that is the reason why we are interested in figuring out if we could do this in a cheap way. So if you want to sell air purifiers to every single house, and you need to be able to run it at low temperature so that you don't have to plug it into your for electricity consumption, and then you want something to be active at extremely low concentrations. So this becomes a challenge both practically for putting up the device, but also from a measurement perspective. How do you measure something that's so low? And then finally, you don't want it to be another sponge. You want it to actually continuously convert formaldehyde to CO2. So in the literature, there's a lot of work around, again, by trial and error, trying to figure out which catalyst might work for this reaction. And the literature usually points towards manganese oxide for being one of the better catalysts at lower temperatures. But manganese oxide itself comes in about 15 to different polymorphs, which have been explored quite extensively for other reactions, but not for this particular one. So you wanted to dig into this to figure out what type of manganese oxide and why would it work for this oxidation reaction. So here's a typical plot of what we'd get from one of these experiments. So here you have how much CO2 is being converted, how much formaldehyde is being adsorbed as a function of time. So under normal dry conditions, what we see is that generally manganese oxide behaves like a sponge. It adsorbs all the formaldehyde, but only roughly produces about 40% of CO2. So the rest is just sitting on the surface and then building up, and it will eventually die. What we found very interestingly is that once you start adding water to this reaction, so it's about 0.7% H2O here, you get really close to 100% conversion. So you're able to run this reaction at room temperature with near full conversion if you add relative humidity to this reaction. So now the question is, what is water doing in accelerating the CO2 conversion? And then again, this is only valid at low concentrations. Once you increase the concentration, the conversion again dies. So there's something really strange and interesting that's happening at about 0.5 ppm of formaldehyde. So as usual, we have a result. We are excited. We want to see what's going on the surface. So we turn again to in situ IR in this case, and then see what are the reaction intermediates as you increase the concentration from 0.5 ppm all the way to 20 ppm. And we see three main features here. There's a water peak, because we have water in the stream. And then we have a formate peak, which is the HCOO. And then there's a carbonate peak, which is CO2. And then we quantify this as a function of time. So what we see is that the carbonate peak forms initially, and then it plateaus off. Same with the water as well. And it is this formate peak which tends to increase with time. And because of the operando nature of these experiments, we're also able to track what comes in, what goes out. And we see that initially there is complete conversion, and then after some point, the conversion starts dropping again, at which point the formaldehyde continues to build. So our hypothesis here was that formate is the one that is poisoning the surface at higher coverages, and it is the CO2 intermediate, which forms initially at lower coverages, that is responsible for the CO2 formation. And we wanted to test this out. We had a reaction mechanism based on spectroscopy, but can we extend this hypothesis to other manganese oxides? Right? So the manganese oxide that I spoke about so far was the gamma manganese oxide. And then what we did was we created a whole library of manganese oxides again. So we looked at about 8 different manganese oxides to see if some of the hypotheses and trends that we saw with one particular manganese oxide, can it be extended as a design principle to optimize the reaction kinetics. And to sort of form a descriptor, we looked at manganese valence, which is a much easier metric to compute relative to the other electronic structure parameters. So we used X-ray absorption spectroscopy to calculate the manganese valence. And then we also use TGA, thermogravimetric analysis, to quantify the amount of water and oxygen in these species. And similar to the experiments that I showed you earlier about adsorption of formaldehyde and figuring out what reaction intermediates form on the surface, we ran the same experiments for this whole library of compounds. And we tracked the relative intensities of the two main intermediates, right? So this is, again, the carbonate intermediate shown in the bottom here, and then the formate intermediate at the top. And interestingly, we see that both of them have sort of opposite trends, and they peak at around 3.8 manganese valence in the opposite way. So the bottom of this is sort of the top of this. This is a really interesting trend. And then when we measure the actual reaction kinetics, so this is the reaction rates at 3 different temperatures, we again find a similar trend in that at around 3.8 manganese valence, we see maximum chemical reactivity. So piecing these two observations together, we could show how maximizing this carbonate reaction intermediate would lead to higher overall reactivity, and that is related to the manganese valence descriptor. Okay, so finally, so far what we've looked at are applications in heterogeneous catalysis. But at the core of it, all of these are surface reactions. So what essentially is happening in both of these examples is that you had CH bonds that were being broken on an oxide surface. And the same reaction happens in electrolyte reactions in batteries. So your cathode material is usually an oxide, let's say like a lithium cobalt oxide, lithium manganese, lithium nickel, so far, and so far. And then the electrolyte is usually an organic molecule containing a lot of CH bonds. So we got curious about, could we use some of the learnings here about how CH bonds break to a use case that is completely removed from what one would typically study in surface reactions, right? So the idea here was not to look at the complete reaction cycle, but predominantly look at the first step, which is an electrolyte reacting with the electrode. This is interesting because unlike in catalysis, here you want the opposite. You don't want your electrolyte to react with the electrode because that will lead to decomposition and then degradation of battery performance overall. So we are sort of looking at an inverse motivation for studying this problem. And we started looking at a bunch of different molecules that I'll introduce, but essentially we're trying to figure out how does the CH bond break. So we had 2 different mechanisms in place. So one is a deprotonation mechanism, where you have the broken carbon fragment adsorbing onto the metal site, or you could have the broken carbon molecule adsorbing onto the oxygen site, which we call it as the oxidative hydrogen abstraction. And then we studied these mechanisms for a bunch of different electrolyte molecules that typically have been used in experiments. And what we generally find is that as you change the chemistry, for example, here from manganese to nickel, or your oxygen 2p band comes closer to the Fermi level, you have more favorable adsorption. So if you're using, for example, lithium nickel oxide, which would increase your battery capacitance, generally speaking, that comes at the cost of increased electrolyte reactivity. So you have this trade-off because these surfaces are generally good at pulling hydrogen from a lot of these electrolyte molecules. Now the question is, which electrolyte should we be using then? So what we did was we developed a whole, again, library of electrolyte molecules. This is an interesting experiment because in the previous 2 studies, we wanted to change the catalyst surface itself. We were changing the chemistry, the structure, so on and so forth for the layer itself. But in this case, we wanted to play around with the electrolytes, so the molecule that is reacting, figuring out how do we optimize that for a given surface. And we tested the reactivity of these 30-odd compounds on the oxide surfaces, and we found a very curious result, which I'll walk through here. So on all 4 of these plots, on the y-axis, you have the adsorption energy. So how much is it taking to break one of the hydrogen bonds on these electrolytes? And then on the x-axis, you have what we are trying to develop are the descriptors. So what explains the reactivity of these molecules? And what we found is that, super clear, it is the energy that takes to replace the CH bond of these molecules with a CO bond, right? So imagine any of these hydrogen CH bonds here. If you compute the energy of replacing that CH bond with a CO bond in the gas phase, that correlates with the adsorption energy that happens on the surface. Why is that interesting? That's interesting because this adsorption energy takes a whole lot to compute. So you have to develop the surface, understand the reaction, figure out the reaction sites, and then get the adsorption energy. But this simple descriptor, you don't have to model a surface at all. You just have to model the reactivity of the gas phase molecule itself. So this gives us tremendous predictive power in not having to compute surfaces, but just having to compute the adsorption, the reactivity of molecules in the gas phase, which is orders of magnitude way cheaper computationally to do. And with this linear trend, we are able to predict a whole bunch of new electrolyte molecules that would have lower reactivity than the current state of the art. So for example, we've identified a bunch of sulfur and fluorine containing electrolytes that are potentially better performing than ethylene carbonate, which is the currently used electrolyte. And then generally speaking, you can extend this approach to a whole bunch of different molecules and reactions. So here, for example, we looked at methanol conversion, CO2 conversion back into methane electrochemically, and then NOx conversion for automotive catalysts. So the idea here is that regardless of what reaction system you choose, one could develop these simple descriptors that help you explain the trends that you see for macroscopic performance. Now the question is, how do we reconcile this sort of simple intuition-based methodology with accelerated machine learning models that are complex by definition? So to give you an example, here's what we've been looking at so far. You have an experimentally measured activity metric, reactivity, turnover frequencies, kinetic rates, and then you had a descriptor on the x-axis, which was easy to explain. And then we've been developing sort of these linear models to explain why, for example, something would show up at the peak of this trend. And then if you wanted more predictive power, you could go a step further and, for example, like the example here, set up a multinomial regression. It's a little more complex than a simple linear process like this, but still you could draw out why certain parameters are more important than others when it comes to reactivity, right? And then finally, you have, if you are looking into like a lasso or a seesaw type regression models where you almost lose out on the explainability, but you gain on how good there are with predictions. So this is sort of a fundamental philosophical debate on what is that we should be doing. So a lot of my work has focused on this approach where you have a physical intuition for why things work and how you can design better catalysts. And then there is the other extreme where you have a lot of predictive power without getting into why things might work, and you might never be able to develop a linear model just the way how the higher dimensionality is captured in these, right? So we've sort of been grappling with this for quite some time to think about how do we integrate some of these workflows into a more fundamental research type of approach. And what we've sort of come up with is using these machine learning models as high throughput tools to narrow down the chemistries and the data sets so that we can still sort of do our descriptive type of work. But now the descriptors are probably called more as features than descriptors. But essentially, you still need this approach to understand why something works or what are the type of features that need to be included when you do some of these screening approaches. Right, so for example, I've spoken quite a bit about DFT and how you set up these surface calculations. They're really expensive. And so Sean from my lab has been working on using machine learning models that have sort of pretty much dismantled DFT industry, I would say, because these are much faster to run, easier to set up. You can run them on your local computer. And pretty much every day, somebody comes up with a new recipe for creating these machine learning models, right? And it's been interesting and challenging to explore some of these to figure out if any of these work. How do they work? Can we implement them in our workflows? To sort of walk through this example, so we have a bunch of chemistries here, rutile chemistries on the x-axis, and we were looking at oxygen vacancy formation energy. And the black trend is the one that comes from DFT. And then generally, all of these machine learning models capture the trend, so they go in the same direction. But you see that there's a pretty big offset depending on which model you choose. So this is pretty encouraging in that this just took probably a few hours or days to run, while this DFT probably took months or years to get to this point. So we're still figuring out how do we actually use this. Can this be used? Can we use this to narrow down the type of chemistries we'd be interested in, and then maybe go back to DFT, but that's still an ongoing investigation. Okay, and then finally, I'll talk about how do we think about active sites beyond just the atomistic approach that I talked about. Right? One area that I've been really interested in is sort of perhaps working a little more closer with our chemical engineering colleagues to bring in mass transport and diffusion effects to thinking about surface chemistry. So how do you integrate diffusion with the electronic structure approach that I've been talking about? And I found this really interesting study where you can, for example, change the interparticle spacing or the interparticle roughness, and that leads to a change in how your selectivity metrics show up. And then you can quantify this using, for example, a roughness factor going all the way from atomic roughness to mesoscopic and macroscopic roughness, and then plug all of that into a single model to capture these effects. So this is one area that I'm really excited to go into. And another area that we are really getting into is doing more community-based work and bringing in all the complexity that comes with it. So we've been looking at biochar, which is essentially an alternative for activated carbon that shows up in a lot of catalytic applications, but using naturally available and locally available resources. Right? So we've had two of my students have been working with 3 partners all over BC and sourcing some of these biochar samples and trying to characterize them to see if they could be applicable for catalytic reactions. And the challenge with such a local approach is the heterogeneity in what you get. Right? So every supplier, every person in the backyard has their own recipes for making these things. And it's been really interesting to use some of the more traditional techniques like spectroscopy to go into people's backyards, take their samples, characterize them, and figure out if they can be used for air purification, water purification, some of the applications that I spoke about in the earlier places. So yeah, that's about it for me. So thank you again so much for listening to my talk, and I hope I've shared something that you can go home to your friends at the library and bar and also talk about these again. And I'd finally like to end with the acknowledgement of a whole bunch of people who've helped with spectroscopy, running experiments at the beamline, preparing samples, running DFT. There's a lot of folks who came together to make this happen. So I'd like to thank all of them and also my lab who put together some of the slides you saw towards the end. So thank you again for listening and happy to take questions.
Thank you very much. Do you have any questions, Ross?